Hello everyone, welcome to today's video, and really we are going to be introduced into a new topic, having done with what we had, that's the trigonometry, and this is similarity. Right, so in this topic, before we take ourselves into the steps of which we need to have some kind of expectation that is it what it is about the similarity. So as such, I'm going to at least give you a lineup of the objectives that will guide us until at the end of the topic. Right, so here with me is the chart that gives us the list of the objectives of today's topic. Right. So once you read, take note of them, and as we are discussing, please make sure that these objectives are being reached. All right, by the end of the topic, you as students, you are supposed to know the following. So you should be able to apply the ratio of the area of, to apply the ratio of the area to calculate the area and sides of similar figures. So here in the similarity, we'll be there looking at issues about the similar figures. I know for sure you have already done something about similarity in Form 2. So here in Form 3, we are just focusing on this section, applying the ratio of area to calculate the area and sides of similar figures. Secondly, we'll be applying the ratio of the volume to calculate the volumes and sides of similar figures. So the target here are similar figures of which we'll be looking at their ratios in order to calculate the area and the sides. So it's about that. Right. So now let us see what is it that we need to know. So here we are there mostly going to know something about the ratios. So what is it about the ratio? Right. So just capture my words in the discussion to see what it is all about this. But remember, this issue about the areas of similar figures in relation to the areas. And then we have to see such issues about the ratios and areas and even the volume are helping us to calculate the volume, the area, and the sides, just like that. All right. Basically, what we are going to be introduced in here are two main things. One, category 1, we'll be looking at what we call the linear scale factor of the similar figures. 2, we'll be looking at what we call of course in 2 categories, talk of what we call we talk of the area scale factor, and then in the same vein we talk of the volume scale factor. Right, this is abbreviated as LSF. Then this one we talk of ASF, while this one we talk of the VSF. So the whole issues about similarity, I'm giving you a guide. So when we begin, you have to know where we're heading to. Issue about similarity here, it's not necessarily about proving that figures are similar. This was already done. But now here we are focusing on LSF in relation to what? ASF and VSF. to make it clear in understanding. Right. So these three issues are the ones that will be there trying to meet the objectives, which I have just highlighted very soon. Right. So now let us begin the course. We are first of all going to look at the issues about the areas in relation to the sides of the similar figures. Right. Let's take this issue step by step. One, let's begin by working on the area, scale, factor. That is the issues related to the sides and the areas of similar figures. That is ASF. Right. What is the area scale factor? First of all, we need to know it. And after we see how we are going to use this area scale factor in calculating up the areas and sides by the objectives which I have just highlighted. Right. Let me just have one pair of similar figures, of which I'll need you to calculate the ratios into fourths. Ratios of the corresponding sides and ratios of the areas of those two figures. And the nature of these figures are that I've said they are similar. So now what I'll do here, there will be an activity that I would perform that will make these figures to be similar, because we don't just come up with figures and say these ones are similar. There must be a condition. So for example, if I might have talk of a rectangle, this is just like an example of a shape. You can also consider other figures, talk of cylinders, talk of triangles, and what have you. So let me use the rectangle. Suppose I've got a rectangle, this one here, described by A, B, C, D. We know for sure that all angles in the rectangle, the vertices of which are 90 degrees. Now, this rectangle has got size described by width, which is maybe 4, and let me have the width as 3, and talk of the length as maybe 5, or whatsoever length you can have. And again, whatever width. You can have yours there. You can decide. You can have 10 as the length. You can have maybe 15 as the you can have maybe talk of a 7 as the width, thing like that. So in my case, I'm having a rectangle ABCD with width 3 centimeters and the length 5. Let us now try to produce a figure that is similar to rectangle ABCD. So for if I'm to produce a figure that is similar to ABCD, one way how I can do that is by just simply enlarging this figure, either to the smaller size or to a larger size. At the end, there is that figure I'll have, which we call it as the image. That one we expect to be similar to this figure we have at hand. Right, so let's try to enlarge this one by a scale factor. Let me write it this way: enlarge this figure A, B, C, D by scale factor of you can decide. I want a scale factor of 2, meaning that this one has to be enlarged twice as much, more like double. So if we are to enlarge this one by a scale factor of 2, it means all the dimension of this figure has to be multiplied by 2, such that if I have the resultant shape of which we call the image, it will be something which has to be magnified. Sorry, these are just sketch with a small bold size think you may just bear with me. Let's just go it by the sketch. But rather, if you talk of the width, we'll be able to tell that this figure has been enlarged to twice as much. So which means I'll have a 2 times the 3, here I'll get a 6. And also 2 times the 5, here I'll get what? 15. Right, so that's what we're going to have there. So now, what is it that we have in this case? What I want to do now is just an issue about a comparison that I want you to do in terms of 2 issues. One, I want you first of all to calculate the area of this first top of the shape and the second shape, where the first shape is defined as an object. When we talk of issue about the enlargement, remember what I've been doing, and then that shape after enlargement is defined as an image. So what I want you to do is first, can you calculate the area of the object and also find the area of the what? Of the image. So if you are there to take the area of the object in this case, you'll be able to bear with me that if we were to wake up the area of this image, you know, for sure, so of this object, you know, for sure this one is a rectangle. You are just there to multiply length times width. So it means area for this one is equal to 5 times 3. And this gives us what? 15. Well, here, if we are there going to take the area of the image, we'll be able to find that the area of this one is still more comes in as 6 times 15. And this gives us what? That is 90. If this one is measured in 30 meters, talk of 90 square centimeters, and this one is 15 square centimeters, something like that. Now, the target here is just a matter of working the ratio. We have 2 figures here. One, first figure we call an object described as A, B, C, D. Take me, right, has got side length as 3 centimeters by 5 centimeters. This one has been enlarged to twice as much. The result is an image, so that here we have like this one as A prime, B prime, C prime, and also D what? D prime. The width, this case now is 6. The length now is 15. But now if I'm there to calculate the areas of the 2 figures, you are in the position that we're able to find that the area for this one is 15 square centimeters, and the area of the image is 15 square centimeters. Now, what is it that now we would like to do with the 2 figures? Right. What we would like to do now is now to work out the talk of the ratios. Right. First, let us calculate the ratio of the corresponding sides. In this case, you know for sure these sides correspond to this one, width to width, and also length to length. And we'll be able to see in this case that if I'm to take the area, talking of the ratios in this case, what I'll have is like this. Now, talk of the ratio of corresponding, talk of the sides. That is a talk of the image, in this case, to the object. I'll take it this way, image to the object, corresponding sides. What I have in this case, it will mean, if I talk of the ratio of the corresponding sides for the image in this case, I'll talk of the width, that is A prime, D prime, that one corresponds to AD. So this one is 6, this one is 3. The ratio here is just like 6 to 3. And again, if I'll have another ratio of the corresponding side, talk of now the length, this one has got D prime, C prime, this one is DC. This side corresponds to this, the ratio of which comes in as talk of what? Talk of this one will give us does it oh no, this one multiplied by what? By 2, or this was supposed to be 10 here. So the area here would have been what? That is 6 times 10. This one gives us 60. Sorry for this one should be 60 square centimeters. Because if this one is 3, this is 5, it should be like, if the scale factor is 2, so you multiply this one by 3, you get a 6. You multiply 2 by 5 here, you get a 10. So now here, if we are to take the ratio, we'll be able to see that the length will give us the ratio of 10 to what? You talk of 10 to 5. This is for the image. This one is for the what? For the object. Right. So here, if you can see that, if you can try at least compare the ratios of the corresponding sides, you find that if I take the ratio of the 6 to 3 and also 10 to 5, you find that what we have here, the ratios are just the same. If I try to simplify here by dividing by common factor for this ratio and that ratio, you find that you have got the common factor, which the 3 gets here 1, there are 2, 5 here 1, 5 here 1, a 2, and the ratio comes in as what? Talk of what? That's a 2 to what? To 1. Right. So this is always true in all circumstances. When you take the ratios of the corresponding sides of the image and the object, that's now talk of the, for the subject in short, which are similar, always the ratios of the corresponding side will always be the same. Like here, right? This figure is similar to this. Ratios of the corresponding sides here, 6 to 3 and also 10 to 5, they're all giving us 2 to 1 is the same. Right, let's put that one aside. And again now, let us now try to consider the ratio of the areas. Ratios of the areas. Ratio of the image, in this case, A, B, C, D, with their primes, to the A, B, C, D as an image. In this case, it would be like talk of the image, area to object area. You'll be able to consider that the area for this one is 60. Area for this one is found like 3 times 5 is 15 square centimeter. So if you talk of the ratios of the areas, it will be 15 to, it will be 60 to 15. If you take the area of the image to area of the object. Now, if we try to simplify this one out, we'll be able to see that the common factor that is A there between the two values, 60 and 15, is the 15, which means 15 can get into 60 4 times, and 15 into 15 is 1. Right. Look at this. What we have just done here, we have done two things. Right. We have calculated the areas of the corresponding sides of two similar figures. This one and that one. And secondly, we have also calculated the ratio of the areas of those similar figures. And what we have here is like the area of the corresponding sides is 2 to 1, and area of the areas is 4 to what? To 1. Right. Be mindful, that is to say, whatever is done here and whatever we're going to come up in this discussion here is true for all figures which are similar. So, and you're really going to observe what we're going to conclude from here. It will be the same for all other areas of concern, as much as issue about area of similar figures is concerned. Right, so here, let us now try to compare. The issue now is a comparison. If I compare the ratio of the corresponding sides and also the ratio of the areas, what is it about them? What is the relationship? Right, so now, allow me first of all to put the two ratios aside and compare them out. Right? We are going to observe that if I try to consider the area of the corresponding sides, which is 2 to 1, versus the area of the what? Of the talk of the ratio of the areas, which is 4 to 1. You find that the two are compared in such a way that say, if I square the ratio of the corresponding sides, that one, it gives me the what? The ratio of the what? The areas. So it's more like is a square of the ratios of the corresponding sides of similar figures is equal to the ratio of the what? Of the areas. So that is there. And we need at least always get to know about this. That's it. The moment I'm given the talk of the similar figures and you calculate the areas of which, you should also expect that the ratio of that one is equal to the square of the ratios of the corresponding sides. Right, so what it means here is just like when I square 2 to 1, that gives me what? 4 to 1. That's what we have it here. Right, and the conclusion that we get from this is just like from the two rectangles that I have, I'm able to conclude this one by the statement which says that talk of the ratio of the areas of similar figures is equal to the ratio is equal to the square. Not necessarily just first of the ratio, but begin with the is equal to the square. Squaring. Is equal to the square of the ratios of the what? Corresponding sides. That's what we have here. Right. So this is an issue that you always need to know, and that it is the target that we have in this topic. Right. So now, let us try now to come up with the definitions of these areas which we observe that their ratios are related in that manner. Right. Now, get to know, that is to say, every time we are taking the ratios of the corresponding sides, the ratio of the corresponding sides is described as the linear scale factor from the beginning of that indicated area. Like in this case, we are talking of the ratio of the corresponding sides, like we are talking of the 2 to 1. This one is defined as a linear scale factor. But now if you talk of the ratio of the areas of these two similar figures, talk of the area of the image to the area of the object, this one is defined as the area scale factor. Right, so it means the area of the top of the image rectangle to the area of the object rectangle. That one is defined as the scale factor. So now from what we have just observed here, the moment we say that the square of the ratio of the corresponding sides is equal to the ratio of the areas, that simply means that from this description there, this sounds like this. That is to say, the moment I will talk of the ratio of the corresponding side, it simply means in this case, talk of the, if we are going to square the linear scale factor, right? That one should give us the what? Area scale what? Factor. That's what it means in this case. Or in other way around, if I would like to obtain the value of LSF in this case, it simply means a matter of just taking the square root of the ASF. Right, so this can also sound in a different way as to say the square, in this case, the square root of ASF, it gives us what? LSF, something like that. Right, so this is what we need to know as students in the first instances about the similarity in book 3 as such. So try just to take it this way, that say what we have done here, it implies to all other similar figures despite the fact here we have used a rectangle. And I think you can be able to produce different types of shapes there where you are for just practice sake, and try to come up with the length of the dimensions of those figures, and then try to get the what ratios of the corresponding sides, and again try again to find the areas. You'll be able to observe that say every time you take the ratio of the corresponding sides versus the ratio of the areas, this is always true. So finally, let me just conclude this way. Each time we talk of the square of the linear scale factor, that gives us the area scale factor. Or we talk of the square root of the area scale factor, that is equal to what? Linear scale factor. Right. So This is what we need to know first. And thank you very much for being together. And I know that you have captured something. But if you have missed something, try just to play the video now and again, and you have to see that where is this conclusion coming from? Because we have had a good activity that gives us into this conclusion. That's the square of the area scale factor is equal to the linear scale factor, or log of the square of the LSF is equal to ASF. Right. So in the next video that we have, you'll be able to see how we are to use this conclusion that we have just made here in order to calculate the areas and the sides of the similar figures by the objective that I announced earlier. As such, thank you very much, and I think we have to be together in the next video.